Hello students, we are done with chapter 1, finally. Let's go to chapter 2. Lessons 4 and 5 are devoted to the chapter 2 of our textbook, the Laplace Transform. The Laplace transformation is a map or an operator or a transformation, it has many names, that sends one real function to another real function where the image function is defined through this improper integral. Now please recall that a function is sending a number to number. We are doing pretty much the same thing. A transformation is sending a function to function. Traditionally, we use lowercase for the original function and uppercase for the image function. And the image function under the Laplace transformation is called the Laplace transform of the original function. The names are a bit confusing, of course, and therefore many people misuse them. So would I. There must be an occasion that I say the Laplace transform while I should have said the Laplace transformation or vice versa, but please just understand me. That's the way things are. Now let's go back to the definition. This Laplace transform, capital Y of S, is defined through this improper integral, and script L is the correspondence, the transformation, or an operator, or a map, which maps the original function, which I'm highlighting in blue, to the image function, blue to red, where the red function is defined through this improper integral. Make sense? So L is sending small y to big Y, blue y to red y. Now keep that in your mind and let's go to the next line, which looks far more intimidating because there are so many characters here, but they mean the same thing. The integral part is the same because they're the same thing. Now what does this mean? The script L is the operator, it's the map or transformation that is sending a function to function. So small y is going to large y. So function value, well, that was poor choice of term, too many terms function. So image function is capital Y. So L of this original is the image. So this whole thing which I just highlighted is the same as capital Y. So this expression, capital Y of S, where I highlighted the function part as red, versus this script L, brace open, and T expression, brace closed. This whole expression here corresponds to the single character capital Y. And of course, S is the independent variable being applied to this function, so S over there. Confusing, yes, but there's no way around it. So you just have to squeeze yourself and make yourself familiar to this thing. There's no way out. We will use this, and we will use these a lot. Of course, early on, I'll try to minimize the use so that you can get used to the underlying concept a little bit more, and then I'm going to use these later on more often. Early on especially, I'm going to use these kind of things more often. I'll use the lowercase alphabets, F, G, Y, and so on, with the independent variable t as the original functions, while the corresponding uppercases, capital F, capital G, capital Y, and so on, and the independent variable s as the corresponding Laplace transforms. It turns out the Laplace transformation is one-to-one, so it is possible to take the inverse map. The inverse transformation is called Laplace inversion, and we use typical inverse map notation to the negative first power. So basically, this Laplace inversion is sending red to blue, so that's precisely the backward. Blue to red is the original, red to blue. So highlight this blue part, and now here's a punchline. I'm highlighting this blue, and that big expression over here, script L inverse, brace open, and S expression, brace close. This big expression corresponds to the single character, small y. Okay, so no matter how complicated thing that I have here with S expression, that just means the function, the original function. Alright, we will have chance to go into these notations and all those, but before doing anything, let's discuss why in the world we are doing this. Let's go ahead with some motivating examples. Here's the first, and this one is a first degree, first order linear differential equation. So you should be able to do this using the method of integrating factor, and it's not difficult at all. Let's see, p is 2, isn't it? P is 2. So the integrating factor is the antiderivative of 2, so e to the 2t power. So multiply this to each term, then it is possible to consolidate left-hand side into a single derivative like this. Y times the integrating factor, and then the right-hand side, this was there before, times the integrating factor. So what do we have? Right-hand side is just 1, and what do you get? Take the antiderivative. T is equal to antiderivative of this, so t plus c. Alright, and then divide away this integrating factor. You're going to get y is equal to t times e to the negative 2t plus c times e to the negative 2t after dividing those away. That's the general condition. And then plug in the initial condition. Y of 0 is 0, so y of 0 is, plug in 0, I get 0 times 1, so that's 0, and then we have c times 1, and that's 0. Okay, c is equal to 0, so that part drops out. Therefore, y is equal to t e to the 2t. That's the solution. That's something we did early on, and I did it really quickly because by now I trust that everybody should be able to do that. Okay, remember this answer because we'll have to come back to it shortly. Now let's pretend that we don't want to do this and we want to use the Laplace transform. How do we do that? Let's begin with a color coding to help you understanding a little bit, and then let's take the Laplace transform of each term. It'll turn out the Laplace transformation is linear, so you can do it term by term. And it turns out that the Laplace transform of y prime and e to the negative t are as follows. Turn out that's the Laplace transform of y prime, and that's the Laplace transform of e to the negative 2t power. So if I applied it to this equation here, small y becomes capital Y upon taking the Laplace transform, and the y prime becomes this blue because of that formula, which we'll probably later in section 2 of this notebook. And green part becomes that. So what do we have? We have an algebraic equation. It's not a difficult equation to solve, so you can solve for y, and we get that, and turns out capital Y is 1 over s plus 2 total quantity squared. Alright, we have it, so let's take Laplace inversion to go back, and if you do that, it'll turn out e to the negative 2t, something we saw before. Oh, it should be negative 2t, excuse me. Yes, it is negative 2t. That was just a typo. Okay, never mind. Two methods yielding the same thing, of course. Now, which is easier? Of course, integrating factor method is easier. Why did anybody do it this way, using all these different formulas? That's why I have another example problem here, which is now second order. In this case, we don't have easy method, at least not just yet. So how do we handle this? Similarly, we take the Laplace transformation of each term, y double prime red, y prime blue, and y is black, and then t squared, that's green, and then we take the Laplace transforms, and then this is for y double prime, that's for y prime, that's for Laplace transform of t squared, and all these formulas, well, just take them for granted. We're going to prove those, but not just yet. We'll do those in section 2. Assuming that you use all those, take the Laplace transforms, red, blue, black, and green. And then black part, y is becoming capital Y, that's good. And blue part, sy minus of y of 0, so minus 1. And then this is a formula for the second derivative, s squared y minus s times y of 0 minus y of 0, but minus minus plus because this is negative. And then the green becomes 4 over t cubed. We have an algebraic equation of y, so we can solve it. And then we solve it. And then we take the Laplace inversion. If you take the Laplace inversion, well, it goes kind of like this. Take the decomposition by partial fraction, like this, and then we can take the Laplace inversion of each, and we have this. That is the solution. Now, the idea is the same. Given linear ODE, take the Laplace transform, and then we get an algebraic equation. Solve for capital Y, and then Laplace inversion. So original Laplace transform will follow some formulas, and that's about it. But solving for y and then taking Laplace inversion here, over here we need some heavy-duty computations, like decomposition by partial fraction, and then looking up the table to get corresponding functions. Don't worry, we're going to get used to all these very quickly, and as for the decomposition by partial fraction, we're going to be using computer algebra systems, so don't be intimidated. In any case, we have tools to solve higher order linear ODEs with constant coefficients. Now, did I say we are going to be using computer algebra systems for the partial fractions? Well, in that case, we don't have to bound ourselves only to the second order. We can go to third order, fourth order, fifth order, and so on, because we're going to be using computers anyway. And that's precisely right. The Laplace transform method goes very, very well with technology. And engineers use it a lot. The kind of examples that go hand in hand with Laplace transform is the linear ordinary differential equation with constant coefficients. It does not matter what the order is because, as I said already a couple of times, more complicated equation, don't worry, computers will handle it. Okay, all right. Before moving on, excuse me, let me just point out a couple of things. We use several formulas here. Things like this for the second derivative, things like that for the first derivative, and the Laplace transforms of some typical functions, special functions. We're going to go through all those in section 2, and we'll prove most of them. I took this from our textbook, but after proving those, most of the time, if not all the time, we'll just go to the table and then just pick up whatever you need and then use it from there. So the Laplace transformation is not that intensive in terms of theoretical understanding. Computation intensive, yes, because of the partial fraction business. Otherwise, not really. Okay, so much for nearly all the things I have to discuss about the Laplace transform and about the introduction of the Laplace transform. And one final topic remains, and that's a kind of optional topic. It goes really deep really quickly. It's this one. Does this improper integral make sense? Certainly not always, because if this y of t is really wacky, then this integral may not make sense. For example, if this y of t is, say, a constant, I can just bring it out and calculate this improper integral with e to the negative st. Take the antiderivative and plug in the top, plug in the bottom, subtract one from the other, that's it. E to the negative infinity is zeros, so no problem there. What if I have polynomial function in there? I cannot take it out, but I can kill it using the integration by parts. It may take 2, 3, 4, maybe 17 applications of integration by parts, but eventually polynomial part will be all killed, and we have exponential remaining. In the end, the same deal again. Plug in the top, plug in the bottom, subtract one from the other. E to the negative infinity is 0. That resolves the problem. If you have some t to the nth power over e to the st, again, it'll go down to 0 because of L'Hopital's rule, some repeated use of L'Hopital's rule. Still no problem. Now, by comparison test, now this may be a bit wordy. Does everybody agree? I mean, does everybody recall this from Calculus 2? Let's see. Now, it's this function y of t is bounded by another function, f of t, and let's say this f of t is well-behaving function like polynomial, or even if it's transcendental, still benign, so that this right-hand side is valid. Then this one is valid as well by comparison test. I hope everybody remembers this from Calc 2. But then again, there are other kind of functions that does not behave nicely. For example, what if this y of t is growing so quickly or oscillating so badly in order of, say, exponential of t squared, for example? That's faster than this exponential of linear order. So this part will not slow down that part enough to squeeze down to 0 toward the end as horizontal asymptote. In that case, this entire thing will blow up. The kind of function that we have this kind of nice behavior are called functions of exponential type, and our textbook author spends quite a bit of space on this discussion and states and proves many fancy theorems about it. Still, that's not the whole complete domain of Laplace transform, but still, it's a worthy discussion. I'm not going to go deeply into that because my purpose here is to use Laplace transformation to solve differential equations, not really studying the Laplace transform itself in terms of the analysis of its properties and so on and so forth. Maybe in a high-level course, but not here. If you're somehow interested, then we can go through your textbook, Chapter 2, the latter part, and Chapter 6. I've seen many textbooks, but our textbook is the best. The Atkins book is better than any textbook I have ever seen as far as Laplace transform part is concerned. So that's a really good book. So if you're interested, go ahead and try that on your own. With fair warning, of course, it's going to be hard, but it may be worth it if you're interested in pure mathematics. Okay, that's where I'm going to stop, and I'll see you again in Section 2 and Section 3.